Good morning. My name is Charles Roeder. I'm going to be talking to you about the overview of the seismic design and behavior of steel brace frames. Okay, as was pointed out earlier, this seminar is going to be broken into three parts. The first part, I'm intending to talk about the general options for brace frames, a different type of systems, and the expected behavior and historical development of these systems. I think this is kind of important because AISC 341.16 provides the seismic design provisions, which are basically the capacity design provisions for each of these systems. I think that the provisions are somewhat like cookbooks, I guess you would say. And I think, as all of us know, that they're rather complex at times, and sometimes cookbooks lead to bad recipes. So what I'd like you to do in that first part is to try to make it clear what we're looking for, what our target is, what the behavior we expect from these various systems, because I think it's important to understand what the target is to truly understand what the provisions are about. So the first part is going to be talking about this overview of these different systems and how they behave. The second part will start to review the provisions from AISC 341.16, and then we'll take a second break and we'll finish up those provisions. When talking about the seismic design of brace frames, probably we should think about ASCE 7 first, because ASCE 7 provides seismic design forces. And it provides some other aspects with seismic design, but I think for brace frames, the forces are the most important issue. And what they do is they lay out the different structural systems, what we have, and when we do this, we recognize we get the seismic design forces. I'd like to be very, very clear. When we do seismic design in the United States, we are not making the structure earthquake-proof. We are designing for very, very small forces, and then we are designing the structure so that it holds together during major earthquakes, so that we get sure safety and economy during small earthquakes. But when that big earthquake occurs, there's going to be some very significant damage to the earthquake, to the structure. And this is what we're talking about very much today, is the design force that we're using and the damage that we're expecting to occur when that big earthquake occurs. So I'd like to be very, very clear to note that if you wish to design a structure so that it remains elastic and suffers no damage in an earthquake, you need to design with much, much larger forces than we're talking about today. Probably forces that are at least 10 times as large, perhaps 20 times as large. So we're discussing the use of these reduced seismic design forces to provide a good economy while assuring safety and minimizing damage and loss. To do this, we have several methods of dealing with it. The most seismic designs are done by the simplistic method of equivalent lateral force method, which is the method we talk about today. And that method has a response modification factor, an R factor. So we're going to be using that discussion of the R factor today because each of these systems has a different R factor, and as a consequence, when we talk about the design, we're going to have to use different detailing requirements to make sure that the structure behaves properly with these various R factors. So the first thing I guess we'll mention is the ASCE 7. We've been asked to use the 2016 provisions. So ASCE 7-16 is the document we're going to be talking about today. And in particular, with ASCE 7, we have this table which describes the R factors for the various systems. And this, at the top of this slide, you see right here, with the top part of this figure, you see this table right here. And this table lists basically 5 different systems. There are really 4, but this bottom system down here, which is a general thing, is one way of designing brace frames. We're going to mention this in passing today. We're not going to be discussing it at all. With each of these systems, you'll see there's various bits of information. There's a response modification factor in this particular table here. And you see the response modification factor for these various systems vary from 3 up to 8. If you have a large response modification factor, you have a relatively small seismic design force. If you have a smaller seismic response modification factor, you have a larger seismic design force. And I think you should note that even with an R value of 3, you really are going to have a fairly substantial amount of inelastic activity during a very, very large earthquake.